Welcome to chapter 4. This is a continuation of the previous chapter, which was related to the flexible pavement design. Now we're going to start with the rigid pavement design. For the rigid pavement design, we're going to go through also another similar method. It's also the AASHTO 1993, which is the American Association of State Highway and Transportation Officials. There's another method that is also out there, but it's not as highly used and relevant nowadays compared to the AASHTO, which is the PCA, the Portland Cement Association Pavement Design Guide Procedure. The one that we're going to cover for this class would be again the AASHTO 1993. So let's get going. The AASHTO 1993, again, it was based on the empirical AASHTO road in 1960s. So if you recall from the previous chapter when we talked about the flexible pavement design, the same AASHTO road tests, some of them were flexible pavements and some were rigid pavements. So you will see there are some similarities between the two procedures, and there are quite differences also between the two procedures. So this is the most common method for design, and it's actually applicable for the three types of rigid pavements that we discussed earlier in this course, which are the jointed plain concrete pavements and jointed reinforced concrete pavements, as well as continuously reinforced concrete pavements. So it will be applicable to design any of the three types of um, the rigid pavements. Again, as I said, there are some similarities to the flexible pavements, but as you would see, that there is also some differences. One of the differences that you'll note is that the pavement strength actually is measured directly by the slab thickness instead of a structural number. If you recall, last time we got the equation, which is the structural number is equal to the thickness times the layer coefficient times the m, which is the drainage coefficient. In this case, again, the nomograph, and instead of giving you the structural number and then you need to get the d, this nomograph for the rigid pavement is going to give you directly the required thickness of the PCC layer. The empirical, again, performance equations that were obtained from the AASHTO test were used and implemented in the AASHTO 1993. But of course, again, there was lots of modifications, and they were extended to make them applicable actually to other regions in the nation instead of just starting and concentrating on one single location. So let's start with some design consideration that we would need to know, similar to the flexible pavement, before we get going with the nomograph. The first one is the pavement performance. So again, we're using the same serviceability index that actually range with time. If we draw here the x is the x-axis the time, and this is the y-axis the pavement performance. We start with a high number when we construct the pavement, and with time, the performance goes down. So the initial serviceability for a rigid pavement is actually 4.5 out of 5, and instead of 4.2 if you recall for flexible pavement. And with time, this is here the PI, and with time, rigid pavement will start to degrade. And now again, we need to define what is failure. Is failure again? Is it 2, 2.5, 3? This is actually one of the similarities between rigid pavement and flexible pavement is the terminal serviceability. Terminal serviceability, as I mentioned last time, is a condition of the pavement at the end of the performance life. So we are willing to wait only till the terminal serviceability reach the value of 3.0 if it's an interstate classification, let's say I-20 or I-40 or I-80. But we can allow the terminal serviceability to go down all the way to 2.5 if it's a principal arterial, or it can go down to 2.0 if it's a local or a collector street. So same thing, we're going to have the delta PSI then, which is the serviceability loss, is going to be equal to the initial serviceability, which is again 4.5 for rigid pavement, minus PT, which is the terminal serviceability. Again, it can be 3, 2.5, or 2, depending on the road classification that we're designing. When it comes to traffic, again, we need to obtain the cumulative expected 18 kip ESLs, which is ESL is the equivalent single axle load. So ESLs actually are calculated by a method similar to what we did for the ASHTO for flexible pavement, except instead of having again the factors that we discussed for flexible pavement here, the load equivalency factors would vary actually based on the slab thickness, which is the D, rather than the structural number. So instead of varying those equivalence factors based on the structural number, now it's going to vary based on the thickness. When it comes to the material consideration, we also gonna um, need to do some material testing, or we need to know about some of the material testing, and the major one that we're gonna spend most of this lecture talking about as a material factor that gets into our design is what we call the subgrade strength. What's the strength of the soil underneath the PCC layer, the Portland cement concrete layer? To characterize that strength, we need to measure what we call the modulus of subgrade reaction, or a K value. The K value is actually, it's something similar to the spring constant that we studied in physics. So here we typically assume that the Portland cement concrete will be sitting on limitless numbers of spring constants across the subgrade or across the soil. So this value, the modulus of subgrade reaction, it heavily depends on, if you could imagine, if it's a spring loaded, it will depend on the moisture content and the soil density. If I have, again, high density soil or low density, if I have moist soil or low moisture soil, this is going to cover the K value. So the K value can be determined if the residual modulus is actually known, and the residual modulus is basically the modulus of elasticity. So we're gonna, again, there are multiple cases here to determine how can we determine the exact amount of the K value. So there are 3 cases that we're gonna start with, and then we're gonna do further corrections afterwards. So the first case for the K, to determine the K value, if we do not have a sub-base. Why is this? Because if you recall the PCC structure, we may have, again, a thick PCC layer, and then I may or may not have an optional base layer. This is base layer. And then on top, at the bottom will be the subgrade. And again, for flexible pavement, having a base or a sub-base is actually, most of the time, it's a requirement to have a strong structure to handle the amount of traffic. When it comes to a rigid pavement, a base layer is an optional layer because the PCC layer will handle most of the load. So in case, so we have one of these cases again, which is case A, to estimate the K value for the subgrade if we don't have a subbase. The second case, which is case B, if we do have a subbase, which is now the base is going to be between the slab, the PCC, and the subgrade. And the third case, if we have what we call the rigid foundation. Rigid foundation meaning that how is the soil layer close to a bedrock? Sometimes, again, we call it there, we try to draw it this way. So how thick is the subgrade? Is the soil is very close to a bedrock or not? And the way we're going to define if we're having a rigid foundation, because if the way we're going to define it is if the thickness of the subgrade is less than 10 feet, meaning that we're getting close to the bedrock. If the bedrock is only 5 feet down from the base, therefore that subgrade is really strong because now it's very thin and we're getting close to the subgrade, and therefore this will have some correction factor for the K, because now the K will vary a lot. If I do not have a base, I'm just gonna have a subgrade. That I need to consider this. If I have a sub base with a subgrade, so these two now we're gonna have to have a representative K value or a spring constant for the 2 layers that's underneath the PCC layer. And the third case would be if I have a rigid foundation, because now if I have a rigid foundation or the subgrade thickness is less than 10 and I'm very close to the rock or the bedrock, then this layer is very strong and the K value will definitely be affected by that. So let's get going with the 3 cases. Let's start with the first case. The first case is the easiest. If I do not have if I do not have a subbase, then the k value can be estimated easily by this simple equation right here. The k value is simply the resilient modulus of this subgrade over 19.4. Again, it's a very empirical equation, but it's that's what we use. So, for example, if I have a resilient modulus equal to 7,000 psi, and there is no subbase, meaning that I have a PCC layer, on top of the subgrade directly, and the subgrade has a resilient modulus of 7,000. The K value for the subgrade is simply 7,000 over 19.4, and that will be equal to 361 PCI. The second case, if I do have a subbase or a base layer between the slab, which is the PCC, and the subgrade. So meaning that again, I have a PCC, and then I have a subbase, and then at the bottom I have a subgrade. In this case, now, as I said, we're going to come up with something called composite K value, because now I do have actually two layers supporting the PCC instead of just one single soil layer. So in order to do this, we're going to go through this figure here, figure 12.18, which is page 574, to determine the subbase. To get to the table, we need to have, again, some inputs to get to the table. So let's have this example here. An example here, the D here always in this part of the chapter represent the thickness. So the thickness of the sub base is 6 inches. So here the sub base is 6 inches. And then I have the modulus of the sub base is 20,000. And then have the resilient modulus of the subgrade is 7,000. We need to do what we need now to obtain the composite modulus of the subgrade reaction. Sometimes we call it K infinity simply because now we're having two layers instead of one. So, and especially again, if we're having an infinite depth of the subgrade, meaning that again the bedrock is far away down, and we're not considering the rigid foundation here. So once we have those three numbers, 6 inches, 20,000 psi, and 7,000 psi for the subgrade, we can go to this interesting figure here. So what we have here on this top part here, we have this is the subgrade elastic modulus. This portion here. So we're gonna pick here the subgrade elastic modulus, which was in this case it was 20,000, which is actually again this is 15, this is 30, so it's gonna be somewhere in between. And then this quarter here, this is the road bed soil resilient modulus. So this is the soil resilient modulus, which was 7,000, which is actually we have a line for it, which is this one right here. Then once we and then this axis here is this is the subbase thickness. So we can have 0, we can have 0, 6, 8, 10, 12, 14, 16, 18, all the way to 20 inches worth of a subbase. In our example, we have a 6-inch subbase, which is going to be this line right here. So once we identify this is the beginning of the process, once we identify that this is 6 inches, I'm going to now draw a line upward and downwards. Upward to match the 15,000 line. Again, as I said, I'm going to stop somewhere between the 30 and the 15, closer to the 30. And here I'm going to draw a line downward all the way to the 7,000. And I'm going to pick this point right here. And then I'm going to draw a horizontal line from this one here all the way to the turning line. And same thing, I'm going to draw a line from the top until they meet at certain point. And that point, those lines actually represent the K infinity, or the composite modulus of subgrade reaction. So this is here, how am I gonna catch and obtain the K infinity equal to 400. So again, if I wanna go back, so I again identified, I was told I have a structure of 3 layers. I have a PCC layer, I have a subbase, and I have a subgrade. So it's two layers, so therefore I cannot go with this scenario because this scenario is without the subbase. Now this is with a subbase. I need the thickness of the subbase, which was 6 inches. I need the modulus of the subbase, which was 20,000 psi. I need the residual modulus of the subgrade, which is 7,000 psi. So I need first again I picked the 6 feet, 6 inches rather for the sub base thickness, and then from this top portion here we need to get the sub base elastic modulus, which was 15,000, and at the bottom portion here I need to get the modulus of the soil, which is 7,000. I'm gonna draw a line upward and downward, and then I'm gonna have a horizontal line until these two lines are gonna match to get the K, which is in this case again we have K infinity from 50 to 100, 200, 300. So they matched or they met at this point here, or these two lines intercepted at a point at the 400 line. Therefore, the K infinity is 400 PCI. All right, so let's move on now to the third case, which is having a rigid foundation. If I have a rigid foundation, which means a rigid foundation below the subgrade and the thickness of the subgrade now. So for the first time ever, we talk about the thickness of the subgrade. We always assume that the subgrade soil is always infinite. But now, if we have a bedrock that is actually close, that's gonna make the thickness of the subgrade less than 10 feet, now we need to put this into consideration, because think about it. If I may have a subgrade, and if this subgrade is so thick on beneath the PCC layer, I'm just gonna get a K value based on case one. But now, if I have a subgrade that is very thin, very shallow, and have now rocks here all over the place, this rocks or the bedrock is going to actually give me an extra stiffness. So I need to accommodate for this. I need actually to take advantage of this, because now having a strong subgrade with a bedrock very close to the surface, that actually will influence eventually the thickness of the PCC layer. Instead of, let's say, needing 6 inches, I may need only 4 or 4.5. So I need to, so this correction, actually you'll see that actually this is gonna pump up the K value that we got from the first step. And I'll show you in a little bit here what I mean by this. Again, we need to get the modulus of the subgrade reaction, K, from figure 1219 and page 576. So this chart again can be applied to slabs with or without subbase, by the way. So case C is actually, you need to ask yourself after applying case A or B. So the very first step, you need to ask yourself, do I have a base or I do not have a base? So if you have a base, you're gonna go, if you do not have a base or a sub-base, you're gonna go to case A and get a K value. If you do have a sub-base, you're gonna go to case B. Regardless, after picking case A or case B, you're gonna go through case C, which is asking yourself, do I have a thin subgrade close to which means that the bedrock is very close to the surface or not? If you have a shallow subgrade, then you need to go through the calculation. And again, these calculations can be through using this structure, which is a PCC on top of subgrade, or I still can have a PCC and a subbase and then a shallow subgrade. If the subgrade again very close to the bedrock, although I have a subbase, it's okay. What I'm gonna do in this case, I'm gonna go through step or step B first, because now I have a subbase, and then I'm gonna correct that using step C. Or if I only have a PCC and underneath it there is a subgrade, I'm gonna go through step A, then step C. All right, so let's go through this example here. To understand what's going on. So we have an example that we need to follow here. Again, I have this as a quick rundown into it, but again, let's explain it one more time. So I have, let's do, we have again, this is the example, it's in your book, assuming that I have a residual modulus equal to 4,000. And this is the thickness now for the first time, the thickness of the subgrade. The subgrade is 5 feet, meaning that the bedrock is at the, again, it's very shallow, and now the thickness of the subgrade is 5 feet, and K infinity is 230. K infinity, again, this is came actually from K infinity came from the previous step. It can be from step one or step two, but apparently, again, the way we call it K infinity, meaning that actually we had a PCC layer on top, and then we have a sub base, and then we have a subgrade that is not that thick. It's actually um, only uh, three. That's actually 5 feet. So PCC, subbase, and subgrade. So so the K infinity came from step B. Assuming again we're done with step B, we have a K infinity equal to 230. Now we need to do a further correction because of having a shallow subgrade. So how can we do it? Again, this axis here is the road bed soil resilience models, which is 4,000. So this is here from 0, this is 5, this is 10, this is 15, and this is 20. So in this case, we have 4,000. So I'm going to go all the way up to reach one of these lines. What are these lines represent? These actually representing the subgrade depth to the rigid foundation. So I can have 2 feet, 5 feet, and 10 feet. As you can see, once there's nothing more than 10 feet, because if you have a subgrade depth more than 10 feet, you don't need to go through this step at all, because now you have a thick subgrade, and the bedrock, if the bedrock is at 10 feet or lower, it's not going to have any positive effect on your design anyways. So in this case, we had a thickness of the subgrade that's equal to 5 feet. So we're gonna go all the way to the line that's fit the 5 feet. Then you need to draw a horizontal line until you hit one of these lines. What are these lines represent? These lines represent the modulus of the subgrade reaction, which is, again, it can be coming from step one if I do not have a subbase, or it can come from step A if I do not have a subbase, or if it can be from step B if I do have a subbase. So you go down, and now it's 300. Please note here that going through this step, if you do have if you have a thin subgrade, the K value will be improved going through this graph or going through this step no matter what, because again, we're here giving more credit to the subgrade if it's very close to the bedrock. So if it's 5 feet, again, which means that the bedrock is very close, therefore the K infinity got improved actually by having the bedrock is very close. It got improved from 230 till 300. We can have again another example here if we want to. Again, if in our, I think this is in our previous example, if you recall, if we have 7,000 here, and we have 20,000, we have 6 inches. This is here assuming we have a sub base, and we came up with the K infinity. The K infinity was 400. So let's do this example. I have here 7,000, and I went all the way up to 5, assuming it's 5 feet. You're going to draw a horizontal line until you hit 400, and this is the 400 line. So it went all the way to this point, and then you need to go down and pick the modified K, and again in this case it's about 500 instead of 400. So again, if you were to go through this graph, the K value that you enter from this graph will be lower than what you get afterwards, because this graph is all about pumping up and giving credit to a shallow subgrade, knowing that the bedrock is very close to the surface. Next step of correction is the effective modulus of subgrade reaction based on the seasonal variation. And this is somehow similar to what we discussed with flexible pavement, but the equation are different, but the procedure are very similar. So this is now the fourth step. So we talked about step A or B. If I have a subbase or I do not have a subbase, you need to pick one of the two. And then the next correction would be if I have if I have a rigid foundation, or if I have a close, if the subgrade is very thin, meaning that the bedrock is close, I need to do the correction. The third type of correction is the effective seasonal variation. So I need to get what we call the effective K value, and instead of effective Brazilian modulus, which we discussed last time, now we need to get the effective K value, which is determined in terms of the seasonal moduli to get the K value. Again, we're going to get a K value for each month. We're going to get the relative damage, similar again to the flexible payment using this equation. And then we're going to get a representative K, or an effective K, for the whole month. So the damage here is equal to the thickness of the thickness here. I think the thickness here for the PCC layer to the power 0.75 minus 0.39 times K for certain month, and then to the power 0.25, all this to the power 3.42. So let's try to understand here what's going on by having an example. So let's calculate the effective modulus of subgrade reaction for a slab thickness of 9 inches. We're going to assume that the slab is placed directly on a subgrade having a monthly Brazilian moduli, and then there is no subbase. So in this case, we're going to have a structure that is PCC, and this PCC, it has a thickness of 9 inches, and then underneath it there is a subgrade. And there is no mentioning about having a bedrock. So if any question that doesn't talk about the existence of a bedrock, you would assume that the bedrock is so deep and you don't need to do that correction. So therefore, again, doing this example, here, this is what we have. You will be provided with the first two columns only. Here we have modulus that was measured for the 12 months, subgrade modulus, variation, similar again to what we discussed for flexible payment. And then we need to get one K value, effective K. So to do so, again, going back to this structure here, you need to go through all the steps that we discussed and ask yourself which one I need to go through first. So I'm going to go all the way back. So the first question that you need to ask yourself, do I have a subbase or I do not have a subbase? In this case, you do not have a subbase, so you're going to go through this step first, which is without a subbase. The K is equal to 0 modulus over 19.4. You're not going to go through step B because you do not have a subbase. You're not going to go through step C because you do not have a rigid foundation. And then you're going to go through the the um, the um, the seasonal variation. So that's why this table here, it has two columns only. The first column is the correction, or to get the K value if we do not have a subbase. And that's why here we're applied the equation, the simple one, which is the Brazilian modulus of that month over 19.4, which will give us the K value for that month. So if you divide 4,500 over 19.4, you're going to be able to get a K value for the month of January equal to 232. If you pick, for example, the month of March, which is again 50,000 over 19.4, you're going to be able to get 2577 PCI as a K value for this month. So once we are again, so here since we have 12 months, we're going to apply this the equation from step A 12 times. Then the next step, again, we're going to jump to the relative damage. I need to get the relative damage for every month because remember, similar to what we did for flexible payment, we're going to get all the relative damage for every single month. We're going to sum them up, get the average, and then put it back onto the same equation to get the representative K value or the effective K value for the entire year. So how to get the relative damage is again using this equation right here. So the D here is going to be the 9 inches, which is mentioned again here. So the D is 9 inches. So 9 inches to the power 0.75 minus 0.39 times K. The K value, which is for the month of January, is 232. And this is all to the power 0.25 and the whole thing to the power 0.3 to the power 3.42. Therefore, you're going to get the relative damage for the month of January equal to 85.7. You're going to do this for every single month, and then you're going to sum up all these months together, and that's what we did here. The summation of all the damages for all the 12 months is 988.7. Therefore, the average damage for per month is actually 988.7 over n, which is in this case 12 months. So we're going to get the average damage equal to 82.4. And then now to get the effective modulus of the subgrade reaction, we're going to use again the figure 12.20, or we can use the same equation. This equation right here, again, that I showed you before. Now we're going to have the damage. Damage, again, we do have the average damage per month, which is 82.4, equal to the D is known. So the U here is going to be 82.4. The D in this case is going to be the 9 inches. And the only unknown in this equation, therefore, will be the K. The K value, the K infinity here, will be equal to 263 PCI. Again, I hope you can go through the example and see again. If you have any question, please reach out to me. The last correction, I promise, the last correction that we're gonna go through for the K value is the loss of support. This happens because the foundation will erode, foundation erosion or differential vertical soil movement. It may affect the again the strength of the soil. If the soil can be eroded if it has lots of fine materials compared to granular materials or gravel materials. Therefore, we need to account for this. So typically, this is mainly a reduction in the K value after we get it from the seasonal variation, which is from the previous step. We need to reduce the effective modulus of the subgrade reaction by a factor called LS, loss of support. Where to get this from? We get it from figure 12.21. It's a chart that's actually correlate the effective modulus of the subgrade reaction we got from the previous step. So this is here the table. So this is the first thing we need to ask ourselves: what type of materials did we use for the subgrade? If it was the best case scenario, if it was cement treated granular base, which means for this subgrade, before we put the Portland cement concrete or before we paved, we actually treated the base or we treated the subgrade with cement. We added 1 or 2% by overall weight of this layer having cement. Therefore, the modulus will be pumped up very high. The modulus typically is going to be from 1 million to 2 million psi, and therefore the loss of support is very minimal, somewhere between 0 and 1. And you're going to understand what does this number mean in the next figure. But the loss of support having again a cement treatment is going to be very minimal because the subgrade or the soil is not going to be eroded that easily if I have cement treatments. I can also have asphalt treatment basis, and the modulus will be somewhere between 350,000 to a million psi, and that's also good. And the erosion would be, or the loss of support would be also 0 to 1. Once we have, now we can have lime stabilization. Lime stabilization is not bad. You can add lime and you can pump up the E from 20,000 to 70,000 psi. And in this case, we may have a loss of support somewhere between 1 and 3. And again, the higher the number, the more the loss with time. And the worst case scenario is actually having unbound materials. Having unbound materials, we can have, or we're going to end up having a high loss of support. If it's unbound granular materials, meaning that it's big gravel rocks, the modulus will be somewhere between 15,000 to 45,000. The loss of support will be 1 to 3. And if you're mainly using fine grain materials or natural subgrade materials, the modulus can be as low as 3,000 to 40,000 at the most, and the loss of support would range from 2 to 3. What these numbers really mean, it actually means a lot if you look at this figure. So what this figure here is all about is this is the effective modulus of the subgrade reaction that we're going to get from the previous steps. Remember again, step A or B, with or without subbase. And then do we have a rigid foundation or do not have a rigid foundation? And the third step, do we have, and then the third step will be the seasonal variation. Once you go through those 3 steps, this is what's going to be represented in this x-axis. And then you need to go, let's say I have a value of 540. 540 is right here, and if I tell you that the loss of support is 1, which is not bad, you're gonna go all the way up to here. What's this line? Again, these lines represent loss of support equal to 0, loss of support equal to 1, all the way to loss of support equal to 3. Assuming if I have a loss of support equal to 1, I'm going to now stop at this line. I'm going to draw a horizontal line, and that will be my very final value for the K, which is equal to 170. Huge drop from 540 based on the previous tips all the way now down to only 170 just because of I'm gonna know that I'm gonna have a lot of loss of support because of the use of certain materials. The only way you're gonna get good results out of this graph is by if I have a loss of support equal to 0. If I have loss of support equal to 0, I'm assuming I got to this table but with 540. I'm gonna go all the way up, and guess what? I'm gonna hit the exact 540 because as you may expect that this line is actually the equality line. The LS0 is the equality line, meaning that if I'm having no zeros loss of support, that means the value that I entered into the graph, which is 540, is what's going to be the final value and from this graph. So let's have an example so I understand this even more. So example here, we have an ASH2 example application of the method for estimating the effective residual modulus. It's an expansive example that we're going to pretty much try to revise and do a little revision of what we've gone through so far. I have a sub-base thickness of 6 inches, and I have the slab thickness itself is 9 inches. The depth to the rigid foundation is 5 feet, and the loss of support LS equal to 0. So you could tell here we're going to go through all the calculations and through all the corrections here simply because I do have a sub base, which means now I have 3 layers instead of 2 layers. I have a slab thickness equal to 9 inches, and guess what? I have even the depth of the subgrade reaction is 5 feet. 5 feet. So if we really want to draw this here, we can. So I have a PCC layer, and the thickness is equal to 9 inches. And then I have a sub base layer, 6 inches. This is here 6 inches. And then I have a subgrade, and this subgrade is not that thick. The subgrade is actually only 5 feet. This is 5 feet, not 5 inches, but 5 feet, but still considered very thin, given the fact that the bedrock is very close. It's less than 10 feet, and the loss of support equal to 1. So let's get going here with the correction. So all what you will be given is actually the first 3 columns, the month, the subgrade modulus for the subgrade modulus, and I'm gonna have the sub base modulus also. Sub base modulus will change by the seasonal variation. So the very first step that you need to do for this example is to get the composite K value. And to get the K value, we need now to go all the way back to ask ourselves, do we have a sub-base or we do not have a sub-base? For this example, we do have a sub-base. So we're going to skip case 1 and we're going to go to case B. Case B is with having a sub-base, we need to go through this figure 1218 and page 574. So which is, it looks similar to this, which we covered in the previous example. So let's go back, and here, how can we get the K value? So first, it's a 6-inch sub-base, as was explained in the problem. And then we're going to go upward and downward. Upward to pick the sub-base elastic modulus, and we're going to go downward to pick what is the sub-base, I mean the soil resilient modulus for the month of January. And we're going to keep doing this for 12 times. So for the month of January, if you recall, we had 20,000 resilient modulus for the subgrade, and we have 50,000 for the modulus for the base layer. So that's why we went again all the way to 20,000 line, which is this is for the subgrade. So it's this line here, and we pick this point, and it's 50,000 for the subbase, which is the third line here. So it's this line here goes all the way until it hit this point. So what we do, then we draw a horizontal line to the turning line, and then until they meet a certain point, and that point would be the K value for this month, the K infinity value for this month, which was 1100 PCI. So that's the number right here. You're gonna do this for now for all the 12 months. So this is the first step. After you get the composite value, the next correction that you need to do is the K value on rigid foundation. If you go again, if you recall going back to the steps here. So after deciding again it's a case B, not case A, then we need to do ask ourselves whether we have a rigid foundation or not. And in this case, yes, because the thickness of this upgrade was only 5 feet. So we needed to go through this type of graph which we covered before. So for our example, we are going to do the same. So once we completed again the fourth column, which is the composite value from the previous step, which was option B. This is now option C, the rigid foundation. So let's pick on the month of July. Month of July, we have 7,000 as the modulus for the subgrade. We have 20,000 as the subgrade modulus for this month, and we have the composite K from previous step as 410. So again, here we have 7,000 which is the modulus of the soil layer. We're going to go all the way up until we hit the line for the appropriate thickness of the subgrade, which is 5 feet. And then we're going to draw a horizontal line until we reach 400. It was 410. So if you see here, this line is for 400 and this line is for 500. So we pick something so basically you're drawing a parallel line here to represent 410, and then we go down and now we pick that the key value based on having a rigid foundation is 540 instead of 410. So, and this was the number right here. We do this also again for all the months as we mentioned before, and that would be the second correction. So the first thing is composite K value, whether case A or B. In this case, it was case B, and then this is case C, well, because we have a rigid foundation. And then the fourth case is, or the fourth correction is the relative damage. To get the relative damage, again, we apply the equation that was provided to you previously, and which is this one right here. We're going to do it for all the 12 months. So, for example, the amount of damage for let's see the first month, which is the month of January, right here. For the month of January, we need the following information: the D, which is the thickness of the base of the PCC layer, which was 9 inch, and we have the K value from the previous correction, which is 1350. So once you plug in these two numbers here to the equation for the month of January, we're going to get the relative damage for the month of January, which is 35. You are gonna repeat this for the entire 12 months. So we have 35 damage, 35 the damage was for the month of January, where the highest was for the month of March, for example, it was 86. And then what we do, which is similar to what we did for flexible pavement, we're gonna sum up all the relative damage for the 12 months, which was 725. We're gonna divide it by how many observations, which were in this case 12 months, and then we're going to get the average damage equal to 60. So now, since we have the average damage per month, now we're going to replace it to this equation. Now we know what's the relative damage per month, and I know what's the thickness of the PCC layer, which is 9 inches. So now the correction, I mean the K value, the representative K value or the effective K value, as we're saying here, the effective modulus of subgrade reaction will be the unknown in this equation. And if you solve the equation, you're going to get the effective modulus of the subgrade reaction equal to 540. Once you do the 540, this is the 540 PCI. Now we're going to do a correction for the loss of support. For the loss of support was told, this is the last correction, loss of support equal to 1. So you need now to go to this graph for 540. You're going to go all the way up for loss of support equal to 1, and therefore the final number will be equal to 170. With this, I think we finished this lecture. Again, overall, we talked mainly about the key value. How can we obtain it using different correction factors that we need to go through, because it's one of the most important factors in the PCC design. And again, we've talked about the thermal serviceability, the initial serviceability, the amount of traffic, which is in E cells, and then the material consideration. Please review the examples that we covered today. And that will be it for this lecture. And again, next lecture, We're gonna have a deeper dive into now the ASHTO design procedure for the PCC structures. Thank you so much. I'll see you next time. Bye bye.